So last time we sort of finished up the last little LQR bits. We talked about infinite horizon LQR. And we talked about controllability for LQR, which is kind of this last little bit of kind of requirements on the problem so that you know you can solve it, right? And we specifically looked at the time invariant case as like a special case, but the sort of analysis we did leading up to that holds in the general time varying case as well. It's just that last trick where you use the Cayley-Hamilton theorem to like shrink that matrix down that is specific to the time invariant case. Okay, and then we talked about dynamic programming, right? And how that was sort of both another lens through which to view kind of the whole optimal control thing that we've been talking about all along, and an alternative way to derive algorithms like LQR, right? From this approach that sort of looks at this like backwards kind of viewpoint and thinking about cost to go functions or value functions, right? And then we talked about how there's a bunch of issues with doing that in general, and how the best we can usually do once you get past LQR is approximate dynamic programming, where we approximate that value function. If you use a neural network, it's called reinforcement learning. If you use a polynomial, it's called numerical optimal control. But that's really kind of, I would say, like that, like how you approximate the value function in the dynamics is really where the differences are between algorithms, practically speaking. Like in here, we're mostly going to stick with like Taylor approximations and polynomials and things like that, and derive, things like Newton and gradient-based optimization algorithms for this stuff. And if you go take a reinforcement learning class, it's basically going to be all about plugging neural networks in as function approximators for that value function or cost to go function, and or Q function, and or dynamics function, and building kind of methods based on those kind of ideas. So neural network, it's deep learning, deep reinforcement learning, polynomial, it's optimal control, but it's really all the same stuff. I hope that's like, I'm trying to get that across to you guys too, that like, we're mostly talking about like the fundamentals here, but this stuff's super applicable across all these domains. And I think it's really good to know the sort of just basic fundamentals of all this stuff when you go and do this stuff. If anyone wants to talk more about RLE things, I'm happy to chat also in general. And it also is a project ideas. If you want to do something that sort of blends those ideas, it's totally cool. Okay, so enough of me ranting about nonsense. Today, we're going to talk first about some background on, so today's really all about making the transition from LQR to constrained problems. So we're going to sort of start this off with a little bit of background on convex optimization and convexity. And then we're going to talk a bunch about Convex Model-Predictive Controller, MPC for short. So who's heard of MPC in here? Just about everybody, right? So this is like, I would say this is the go-to control algorithm in modern robotics. Like almost every system you encounter, like autonomous cars, legged robots, SpaceX rockets, like everybody's doing MPC. It is kind of the go-to control method in modern robotics. So this is like super practical, super relevant stuff that you're likely to see in just about any like deployed robotic system today, I would say. So it's really good stuff to know about, and hopefully we can kind of get you some good exposure to in this class. All right, so let's do it. So let's, so as just kind of like some bridging the gap here, kind of like from LQR, like why are we doing this stuff and why is this useful? So like just kind of basic Convex Mpc background. And why would you want to do this over LQR? So it's really all about handling constraints, right? So LQR, as we saw, like it's very powerful. It can be applied really well to highly nonlinear systems, actually. So you can use LQR on all kinds of things, super useful. But it assumes that you don't have any constraints on the system. In particular, the most common constraint that you'll deal with in practice where LQR can start to fail on you is when you have torque limits or other kind of actuator limits, like torque or thrust limits. If you're hitting those limits, the controller is not reasoning about them at all. So if you end up saturating your actuators, very often your LQR controller will fail on you. And this is sort of trying to get at that. And so let's see. So often the constraints that we really need to worry about, they're often really simple. So like the most common one, right, are these kind of actuator things. And those can almost always be encoded as a convex constraint or a convex set. So actuator limits are simple bounds usually, right? Torque limits. Usually thrust limits are also nice and simple and can often be written down as cone constraints. A lot of other things. So that's it. And then basically the message is constraints, right, break this nice Riccati LQR solution that we've been talking about. But if I'm thinking about this as the kind of the QP formulation of LQR that we talked about before, right? QPs can have linear inequality constraints, right? So I might not be able to use the Riccati solution and the nice K matrix, feedback gains, but I can still just go solve the QP. And as long as I can solve that QP fast enough, this is totally tractable and I can run it online. And it turns out in modern, with modern computing, we can often solve those QPs at kilohertz rates. So you can really run these things online on robots and it works really well. And part of the reason this is so common now is just that computers have gotten fast enough to actually do it in real time. Okay, and let's see, basically, yeah, that Convex Mpc has gotten super popular. And like kind of the story of MPC over the last several decades is basically it getting moved into more and more domains where as the computers have gotten faster, and it's really like how fast the dynamics of the system are. So in the beginning, it was used in the chemical process control industry on chemical plants where the dynamics, like the control update rate might be once or twice a minute. So you have like, 30 seconds to solve your optimization problem, your QP, right? Now we can do it at kilohertz. So now you can put it on a quadruped or a rocket or something, right? So that's kind of the story. Okay, so that's that kind of like introductory motivation, let's say. Let's kind of like dig in now into this convexity set of ideas. All right, so the first thing to know is what is a convex set? And who's got a good definition of a convex set? Nobody? Okay, I'm gonna draw two pictures. Oh yeah, you got one?
It's a set whose like the convex combination of all elements within the set are.
Okay, so that's a slightly circular definition that involves, the word convex in the definition. So I'm gonna draw you two pictures.
Did you say
Tell me
like
which one of these is
line
convex and
between
which
any
one's
two
not.
points, like is in the set?
Sorry?
The line between any 2 points is also in the
Yeah,
set.
our Zoom friend just said the thing I'm gonna say. So basically the definition, a good working definition is it's a set such that if you pick any 2 points in the set and draw a line between them, the entire line is contained within the set. So in this particular case, right, I can take, say, point, any 2 points in here, draw a line, the line's still in the set. This shape, however, if I pick a point over here and a point over here and draw this dotted line, it leaves the set, right? So yes, check. bad X. So, okay, the definition is a line connecting any 2 points in the set is contained in the set. Okay, questions about that? Everyone cool with that? You guys have all probably heard of this before. Okay, so some standard examples of convex sets that are super common in optimization that actually get used in this kind of control context. We'll list a few for you. Okay, so simplest one would be a linear subspace. So this would be, if you wrote this down as a constraint, this is AX equals B, which is, by the way, how we write down our dynamics, right? Our linear dynamics. Linear dynamics equal linear subspace equal convex set. The next sort of most common one would be half spaces or boxes or polytopes, all of which are linear inequalities. So let's write this down. Half space slash box slash polytope. This would be AX less than equal to B. Does anyone not know what all those words mean? Everyone good with that? So yeah.
What's a polygon?
Polytope is the n-dimensional, like higher dimensional version of a polygon. It's just a shape that's got like planes on all sides, right? It's just the like hyper, like once you get past 2D, right? Polygons in the plane, polytope is in 3D, 4D, 5D, et cetera, right? So it turns out, yeah, in general, an AX less than equal to B thing like that, it defines a polytope in general as that's like the most general shape you can have from that kind of inequality. Does that make sense?
Yeah.
Cool. Okay. And then we've got another super common one, are ellipsoids. So these are quadratic inequalities. These look like X transpose PX sort of things, like X transpose PX less than equal to 1, say, where P is positive definite. So that's a good one. So this is like egg shapes, right? Oval things, but in n dimensions in general. And then the last one that are super common and super useful, it turns out, in a lot of control applications are cones. There's lots of different kinds of cones. The kind of cone I'm talking about is called the second order cone. We'll write this down. It's the one you think. It's like the ice cream cone shape that we're all used to. So it looks like if I have a vector X and I take out the sort of first element, and then I take the rest of them. So elements like 2 to the end. If I take the 2 norm of that and set it less than or equal to the first element of the vector, turns out that defines a cone. So the cone axis is whatever the x1 axis is, basically. And then saying all the directions perpendicular to that have to have norm less than or equal to how far along that other axis you are. That makes sense. You can generalize this. You can put matrices in there and other things to like change the direction of the cone and stuff like this, but that's sort of like a pretty good working definition. This is called a second order cone. It's called second order because it has a 2 norm in the definition. Turns out you can use other norms that'll give you other shaped cones and stuff, and they're still cones, but this is the normal one that we usually use. And yeah, this is the one you think. It's also called the Lorentz cone. Well, whatever, I don't know, there's different names. Okay, cool. Any questions about that? Sort of standard convex shapes that we're used to that end up being useful sometimes. Okay, next thing to define is a convex function. We got convex set and convex function. These are the 2 ingredients. So a convex function is, so yeah, anyone want to give me a definition of a convex function? Yeah. So yeah, that's a pretty good one. I think that works. So there's another way of saying that, which is maybe the more standard way. It's a function whose epigraph, which is everything above the graph, is a convex set, which I think is equivalent to what you just said, right? Secant line is take any 2 points, connect it, right? And that's got to be, so that's the definition of a convex set. So yeah, that's a good one too. Okay, so in particular, this is for scalar valued functions. So it's a function f of x from Rn to R, right? So it's a function that eats a vector and spits out a scalar, also known as a cost function for us, right? So we're specifically talking about here like objective functions or cost functions that we're trying to minimize. An epigraph is the set that's defined by like everything above the graph. So we'll draw a couple of pictures. So like the quintessential one is like a quadratic that's got a positive definite Hessian, right? So stuff like this. So I take this thing and I think about like, you know, the epigraph is everything up here. And then if I do the, you know, sort of 2-point test, you know, this is always going to be true, right? So yay, check, or rather, that should be a green check. And then if we draw like another, you know, sort of less nice example would be something like, I don't know, like this, that's got sort of wiggles in it, right? That does something like this. And this epigraph looks like this. And over here, right, I can pick 2 points that when connected are not inside the set. So this is bad. Cool. Okay, so standard examples of convex functions that we'll see. Are basically, yeah, go ahead, sorry.
Yeah, I guess I haven't really thought about this before until you mentioned it, but are convex functions only mapping to scalars?
Yes.
Okay, so if you have like one that goes from Rn to Rn, it's not convex, or like there's no way, like even if it's like something like a linear function.
Yeah, so basically like we don't think like the definitions are for functions from, the definition of a convex function is from Rn to R. So like there's not really a sort of like, yeah, the definition just doesn't make sense in the like Rn to Rn context.
Got it. Yeah. Yeah. I tried thinking about it and I was like, I couldn't come up with like a similar thing.
Yeah. Okay. So convex functions that we'll see, linear ones. So this would be f of x equals c transpose x for some c. That's a convex function. The kind of classic one in optimal control that we almost always use as our cost functions are quadratics. So this would be f of x equals something like 1/2 x transpose qx plus a linear term. And again, positive definite q makes it positive. You know, the other one that's super common are norms. Any norm is convex, it turns out. So like f of x equals, you know, norm x, and it's any norm you want in there. Lots of other ones, and you can compose these, right? So like a sum of convex functions is convex, stuff like that. There's like some other rules for making more complicated ones up, but generally speaking, there's a handful of like basic building block ones that that we use all the time. These are pretty much the ones you'll see in like a control context. Yeah.
Do they have to be bounded away from negative infinity?
So
X cubed is that?
This is a good question. So x cubed is already non-convex. So that's maybe not the best example. But
It's just right?
well, it does one of these, right? I guess you could make one that's sort of, so I think like it doesn't have to be, I think the definition of convexity does not preclude functions that are bounded away from negative infinity. And so if you like study convex optimization, there's these like generalizations of minimum and maximum that you'll see, like infimum and you know, these kind of things. And that's to include like these possibilities for infinities. So yeah, I think that's fair game, although not useful in practice, right? So you would say if you wrote down a problem like of that flavor, we would call it infeasible, right? Like if the optimum is at infinity, then like, you know, we don't like that. So I would say you don't want to write a problem like that down in a control context. Anybody else? Okay, cool. So that's convex stuff. Convex optimization problem then is minimize a convex function over a convex set. So you have a convex function that you're minimizing subject to convex constraints, where the constraint set defines a convex set. That makes sense? Okay, so standard examples of convex optimization problems, which we have solvers for. In particular, there are like good, you know, solvers for these problems that give you guaranteed answers and things like that. So the first one are linear programs, or LPs. By the way, program is an old word for optimization problem, basically. You'll hear this all the time, right? So yeah, that's why these things all say program. So linear program is, unsurprisingly, linear F, linear constraint, linear C of X. One we've already seen is quadratic program. So this is also known as a QP, and this is quadratic F, linear constraint again. Okay, so the next sort of one up the hierarchy, if you like. So there's sort of a hierarchy of these convex problems. Basically, an LP is a QP, right? It's just a QP without the quadratic cost term. Similarly, there's sort of the next one. We'll talk about our quadratically constrained QP. So also known as a QCQP for short. And this is a quadratic F and quadratic C, specifically a convex quadratic, which is an ellipsoid, right? So think about it geometrically. And then the next one up so QCQPs show up, and QPs are a special case, right? Again, there's another one that's actually super common in MPC applications that shows up quite a bit that are called second order cone programs, or SOCP. And that is, unsurprisingly, the constraint set is a cone. The standard form of that actually technically has a linear f of x, but you'll often see them with quadratic f of x as well. And it's easy to transform one into the other, it turns out. So yeah, it turns out cones end up being surprisingly common as constraints. So these show up quite a bit. Let's see. Okay, so any questions about that stuff? Yeah. Yeah, so linear program, everything's linear. Linear cost function / objective function, the f of x you're minimizing is linear. And then the constraints are also linear. QP is the ones we've already looked at. So those have a quadratic cost and a linear constraint set. Then quadratically constrained QP is what it sounds like. It's a QP that's allowed to have quadratic constraints as well. So quadratic cost, quadratic constraints, convex quadratic constraints, which geometrically are ellipsoids, turns out. And then second order cone is now you're allowing conic constraints, cone constraints on top of the rest, right? So each one of these is sort of like a special case of the one, of the ones above it. is a way to think about this, right? All right. Any other questions about this? So roughly speaking, there's good solvers for all of these. And if you can write your problem down as one of these standard forms, you can get an off-the-shelf solver to solve it. And as long as it's not insanely huge, you can probably do it at real-time rates and like do this on a robot. Is sort of a good rough first order way of thinking about these problems. Yeah.
Is an ellipsoid like a subset of the cone?
Yeah. So remember the cone, it's 2 norm less than some other element of the vector. If you fix the right-hand vector, then it's just an ellipsoid basically, right? Modulo some extra massagey tricks of like, if you want it to be a weird shape, right? Like you have to introduce a matrix in there to morph the shape. But generally speaking, yeah, QCQPs can also, convex QCQPs can always be written as a second order cone problem. Yeah, it's not necessarily super obvious, but if you sit down and work at it, you can figure it out. It's not too bad. All right, cool. Okay, so that's that. So why do we care about this whole convex thing? So in general, right, these are nonlinear things, right? We have quadratic functions floating around and stuff like that. Why are these useful? Why do we care about this whole specialization to convex things? People in the room know. Yeah, so the gist of this is, and it's kind of obvious if we go back and look at this picture. So if you look at a convex function versus a non-convex function, that non-convex function has potentially multiple local optima, right? Like that one I just drew has 3 local optima, right? That I could potentially get stuck at if I'm doing Newton's method. Whereas the convex one turns out for a convex function, just the way it's set up, if any local optimum is the global optimum. So they cannot have spurious local optima is the deal. Okay, so that's why they're interesting and useful. Basically, by construction, they only have a single local optima, and it is the global optimum. So basically, yeah, if you use a solver on one of these and you find a point that satisfies the KKT conditions, you've got the global optimum. So that's nice. And then like from a practical kind of control engineering perspective, the upshot of this is that Newton's method works really, really well, really fast and super reliably on these problems. So for all the problems we just talked about, I can write down a Newton's method kind of flavored solver that will converge in like 5 to 10 iterations max on any problem instance you hand me. And therefore, I can like guarantee that I can get you the solution. I can bound the time it's going to take me to get a solution, and I can run this stuff in real time at like guaranteed rates. So for control, online control stuff, right? Let's see. And so, yeah, this means cool. So all that stuff we talked about before with like regularization and line searches, and we talked about local optima where you can get stuck and all this kind of stuff when you're doing Newton's method, basically none of that can happen on a convex problem. And Newton's method will just like barrel right to the solution super quickly. So that is, so they're safe to use online is basically the result of all that. Any questions about this? Yeah. So I mean, like, I know how big the problem is, right? So I know like what the state dimension is. I know what the time horizon is. So I know how big the problem is. And I know I know it's not going to take me more than, say, like 10 iterations max of Newton to get there. So I can tell you with like certifiable guarantees, if you hand me this problem and you want to solve it online, I can count up the number of floating point operations, and I can know the processor speed, and I can tell you it's going to take you at most 2 milliseconds to solve any problem that you of this form, right? Given your system dynamics and your constraints and the computer you've got on board, I can tell you exactly how long it will take max to solve the problem. Does that make sense? Because in general, for a non-convex, nonlinear problem that I use Newton's method on, I can't do that. I can't bound, like, it could take 5 iterations, it could take 2 iterations, it could take 100 iterations. I have no way of knowing that in general, right? But for these problems, if you do it right, you can basically say exactly how many iterations you'll need as an upper bound. And then you can say, I know how much each iteration costs, and like, therefore I know how long it's going to take to solve the problem. And then you can say, okay, now I can guarantee you that I can run the controller at 50 hertz or something like this, right? Yeah. Did you have something, or are you just generally yawning and stretching? It's fine. Sorry. Okay, anybody else? Yeah.
So the objective function is going to be inherently convex or non-convex.
Yeah. And so the important thing there is we get to pick that, right? Like in control engineering, like the objective functions are costs that we're writing down, right? So we can pretty much always make that convex. The part that we can't are the dynamics, which are usually nonlinear, and often the constraints, we don't get to pick those either, right? So like the physics, we don't get to pick. The cost function, we get to pick, right? So practically speaking, we almost always choose convex cost functions. Like we almost always use quadratics, right? Because they're convenient. So that we can help, like we can do something about that. The rest of this, we often can't help. It's just what it is, right? So there's a lot of tricks and games that you can play to try to massage the problem to get it to be convex. And that's like a lot of approximations, right? And things like this that you can play. The simplest one is linearizing the dynamics, right? But there's a lot of other games you can play as well. Anybody else before we keep moving? All right.
If you do a second order Taylor approximation of say like a non-convex dynamics function, is that one way you could turn it into a convex constraint?
Sometimes. So yeah, that's a fun game to play. Sometimes you can. So the question was if you have like a second order Taylor expansion of your dynamics. So that's a quadratic equality constraint, right? So we said, the only ones that are legal from a convex perspective, if they're equalities, they can only be linear equalities. You are, though, allowed to have quadratic inequalities, right? Like the ellipsoidal kind of stuff, the QCQP, and the conic stuff, the SOCP, those are quadratic inequalities, right? So it turns out there are some problems where you can have a quadratic equality constraint, like from your dynamics, that you can relax into an inequality. And then with certain magic tricks, you can still get it to converge to the exact answer. It's called a convex relaxation. And like, we can talk about that if you want. This is getting into like research tricks, but there are ways of doing that.
Hey, quick question about that.
Yeah.
Just, negate it and then just write like both sides of the inequality, like if it's an equal, and then just solve it like normally.
So that doesn't work for the, if you do, you can try that for the quadratic case. What'll happen is one side of that will be convex and the other side will be concave. And
right.
It doesn't work, right? You can't have both of them.
Right, yeah. Makes sense. Yeah. Okay.
Cool. Okay. Anybody else? Well, until we move on, we good? All right, so let's do it. So now we're going to do the MPC story. And just FYI, yeah. So that was like the crash course in convex optimization. There are entire courses in that. So like, maybe, like think about taking one of those if you're into this. But, this was the I don't know, half-hour introduction to something that is usually a whole semester course. Okay, so let's see. So the idea here, this convex MPC stuff, generally speaking, the way to think about this is as constrained LQR. Like generally, we're only able to here use linear dynamics, right? Because the equalities have to be linear, but we can have all these nice constraints on states and controls and stuff like that. So really think about this as a constrained version of LQR. What else do we say about this? Okay, so here's like kind of, I think the right way to think about this in your head. And the reason we did it in this order, so we're going to think about this as really as like approximate dynamic programming. So remember from the DP discussion last time, basically from dynamic programming, like if we have the cost to go, if we know the cost to go, then to get the feedback policy, we only have to solve a one-step optimization problem, right? We just have to solve an optimization problem with the current state, the current step cost, and then the cost to go for the rest of the trajectory, right? Remember this? This is how we derived LQR. Okay, cool. So let's write that down. So we can do this one-step problem. So UK equals argmin over U of one-step cost plus cost to go with the dynamics plugged in. Also, this whole thing is also the Q function from RL, right? If you want to call it that. Okay, so this, we can, if I plug this in for LQR, I would get 1/2 U transpose RU plus sort of the dynamics AXK plus BU, we'll put some Ks on these, I guess, transpose PK plus 1, oh, there's a 1/2 up here, sorry, times, you know, dynamic stuff again. Cool. So that's just that expanded out for the LQR case, right? Where we have a quadratic cost to go, quadratic, you know, everything, and then linear dynamics plugged in. So looking at that right now, I'm taking a min over U. If I just cared about input constraints like torque limits, right? I'm solving this one-step minimization problem. Like a pretty obvious move here would be to just put the constraints on U in this problem, right? And solve this one-step problem with my torque limits. You want to follow that? So we could do that. But it turns out that doesn't perform super well. And in fact, may kind of perform very poorly and blow up on you. Why is that? Anyone have any thoughts on why this might do poorly? Yeah.
The cost to go is kind of incorrect because kind of the cost to go for different policy.
Exactly. Yeah, that's exactly right. So the cost to go here from LQR is computed ignoring with no constraints, right? So the cost to go is ignoring all those constraints. So like it's totally wrong, basically out into the far future, right? Okay. Okay, so that sort of motivates our next move. So the idea here is like, okay, well, you know, if I'm doing this LQR thing, like, okay, that cost to go is maybe like really bad if I'm just railing against my torque limits. But assuming that the system is well behaved and stabilizable, and that I'm going to, you know, eventually drive it to the origin and all that good stuff, my controls, you know, out in the future at some point should you know, get off the constraint boundary and like settle down, right? So the idea here is like, well, far enough out into the future I should converge to a part of the state space where the controls should back off the constraint boundary. And then at that point, that LQR cost to go will be a good approximation, right? Okay, so the idea here then is looking at this problem, I'm doing this one-step minimization. There's no reason, there's nothing that says I can't take that over like 2 steps or 3 steps or 4 steps and then plug in the cost to go, right, at the tail. So the idea here is I'm basically going to take this one-step problem from dynamic programming. I'm going to start adding more time steps ahead of the cost to go. And that's called the horizon. I can take that out as far as I want. And in general, the farther I take it, the better for performance reasons. But yeah, like if you take it out far enough, you could imagine like basically getting to a place where the long tail is reasonable, is reasonably approximated by the unconstrained LQR solution. Is that everyone cool with that? All right. Yeah, so the problem with the one-step thing is it's like pretty myopic, right? And the cost to go that I'm using there after the one step to get the rest of the trajectory is not accounting for any constraints, right? But if my system is well behaved and I think I can stabilize it and drive it to the origin and all that good stuff, basically like if I go out far enough into the future, if my control policy is working, it should drive the system towards, remember the goal here with like an LQR problem is to drive everything to 0, right? So far enough out into the future, if things are well behaved, I will be able to drive the system to the origin and drive those U's towards 0, right? And at that point, it'll back off the constraints, right? So if I have torque limits, I have a U min, U max kind of thing. If right now I'm hitting those constraints, if the system's well behaved, like 10 seconds from now, I should start to see it come down, right, towards 0. At that point, once I'm off the constraint, then I'm back to like standard LQR land, right, with no constraints. And at that point, the cost to go is a good approximation, right? So the intuition is that like, if I take this horizon out longer than one time step in this dynamic programming setup, if I go far enough out before I use the cost to go, by that point, if I'm off the constraint, then the cost to go is right. Does that make sense? Cool. So here's the setup. So I'm going to do, it's going to look like a sort of almost the standard LQR problem. I'm going to have min over x, we're going to call it 1 to h, and then u 1 to h minus 1. So h instead of n is basically the only difference. And then everything else in here is going to look like standard LQR. And then we're going to have a terminal cost. And the important thing is the terminal cost here, right, is basically so that at that h, I'm going to plug in the LQR cost to go at the end. And, I'll put an h on this. I don't know, this sort of, but the idea is that this thing is approximate of the long tail of this thing with the LQR cost to go, right? And then I can now put in, all the usual stuff. So in particular here, we'll have our dynamics constraints. So this is still standard LQR, right? But here's where it gets different, right? So now I can do xk in some convex set, and then uk in some convex set. And as long as those are convex, this is all good and I can solve it reliably. And, examples, right, would be, so like, any of the sets we talked about when we talked about convex sets, but like, the most standard one would be like torque limit kind of stuff like this. Right. But yeah. Those are the cost weight matrices from LQR. So quadratic cost terms. So X transpose QX for the state cost, right? U transpose RU for the control cost. And those have to be, Q has to be positive semi-definite and R has to be strictly positive definite for things to work nicely. Right, so P is the cost to go from LQR. The quadratic cost to go from the LQR solution, right? From the Riccati solution that we talked about last time. Yeah.
Are you sort of forcing it to go away from the constraints at every step?
We're not forcing it, but the cost function is trying, remember in LQR, the cost functions are trying to drive everything to zero, right?
But then is it just better to update the constraint after every step? Instead of human, for example, this one, the top limits.
Yeah.
What if you have some U1 and U1 max? U1 min, U1 max, which is for the first step. Then you have U2 min, U2 max, where U2 min is greater and U2 max is lesser than.
So those constraints are we don't get to pick those. Those are usually coming from like your actuators on your real robot, right? Like those are physics.
Yeah, but so as long as you stay within those bounds, you can sort of change the constraints to an inner set.
Why would I do that?
Make it converge faster.
So basically, this is like my motor can produce like 10 Newton meters of torque, right?
Yeah.
In general, I want to use all that torque to like make my robot do cool things, right? I don't want to like handicap the system unnecessarily, but the motor can only do so much, right? You might have other related things for safety reasons, right? But like generally speaking, you want to exploit the full capability. So I don't want to set those artificially smaller than what the actuator's torque capability actually is usually, right? So those, like the way to think about it, these constraints are things that you don't get to choose. They're things coming from the hardware, right? That you want to encode in the controller somehow. Think of them like in the same vein as the dynamics, right? They're like part of the system model, right? Part of the really kind of, in the case of actuator limits, they're really kind of part of the dynamics, right? Yeah.
If you like were to give it some set point that like required a steady state input that like was unreasonable for your torque limits, then would this just fail, basically?
Yeah, this would probably barf at you and say it's infeasible. So yeah, you want to make sure you don't do that in general. So one thing that I should mention, right, we talked about all this convexity stuff, right, and said that like kind of they don't have any spurious local optima. They can still be infeasible, right? You can write down a non-convex problem trivially, right, where the solution is like there just isn't a solution, right? So like the dumbest version of this would be something where like you end up like writing down a whole bunch of mutually exclusive constraints, right? If I say like you have to be in this half space and in this ellipsoid over here, you can't, right? It's impossible. There's no intersection of those sets. So like you can write down trivially an infeasible convex problem that has no solution. That's still totally possible, right? All this says is that if you write down a feasible one, I can find you the solution fast, right? So you still have to like be a little bit smart about the problem setup. Yeah.
And you said like you don't want to like unnecessarily like limit how much you use. So do you like dynamically change how long that H is to make sure that you're still being as like greedy as possible?
Yeah. So in general, this is a good thing to talk about. Actually, we're going to talk about this right now. So like generally speaking, like you want to make the H as big as you can. You get better performance with a bigger H. The reason you have a shorter H is compute limits. It's like you need to be able to solve the problem fast enough online, and that's it. Yeah. No, generally not. If you're talking about solver iteration convergence, no, not at all. So generally speaking, modulo some details, like for a convex problem, like for a given solver implementation, like a given solver type of solver, basically the number of Newton iterations for a convex problem is roughly fixed. So like if I write a nice primal dual interior point solver, basically it's going to take 5 to 10 Newton iterations regardless of the problem size or any of those other details. It depends more on actually on conditioning, numerical conditioning than any of that other stuff, than like problem size. Yeah.
So first, what I can understand is that with the constraint LQR, we just plan everything from the final, and then with the MPC, we just go ahead again. So we start backwards and then we
Yeah, that's kind of right. Yeah. So yeah, in particular, right, you would be getting this cost to go approximation from a backward Riccati solution, assuming no constraints, right? And then in the forward setting, you'd be doing this with the constraints in there, right? And theoretically, right? Okay, so yeah, I'll talk more. We're going to talk about some other stuff. I don't want to get too ahead of ourselves. Is that everyone cool? We keep going. All right. So let's see, things to say here. So this is our setup. This H that we have in here, I already said the word, so that's not a surprise. It's called the horizon. And in general, this is like, less than the big N, that we maybe originally had for the problem. Let's see. So this is without any additional constraints. So if I don't have any additional like state and input constraints on this problem, it is just the LQR problem, right? And so in that setting, this MPC setup exactly matches LQR. If you're not on the constraint, then it's exactly the same, right? So this is MPC. This is also known as receding horizon control, by the way, for obvious reasons. For any H, right? Basically, if you don't have any constraints, the H doesn't matter, right? Because like that cost to go is exact. So 1 step works, 10 steps works. They all give you the same answer. Let's see. So yeah, and then just to like write down that like sort of intuitive explanation I was giving before, basically. So this like explicit constrained optimization over the first H steps is hopefully getting the state close enough to the reference or origin so that the constraints are no longer active. Right. That makes sense, everybody? I said that a couple times. Okay, so yeah.
So like, what if it doesn't, right? Like, is it worse in this case to include that extra LQR?
No, okay, so you need that term always. So you always, when you do MPC, you always need some cost to go approximation at the tail of the MPC horizon. It can be a bad approximation, but you always need something there to approximate the long tail, right? Because you're basically doing this myopic optimal control problem, and you need something to inform, what the tail is past the end of the horizon in general. You need some cost to go approximation. This is sort of the intuitive thing in this LQR context, but in general, you always have to have something there. And this is kind of the next thing to say. So here's the sort of a good approximation of the value function or cost to go is always important to have good performance with an MPC implementation. This depends very much on the problem. So some problems you can get away with a terrible approximation. Some problems you need a super good one, and it just depends. Okay, what else? So basically the idea here is the better V of X is as an approximation to the true cost to go, the shorter horizon you can get away with, right? Because basically if it's in the limit of it being the exact cost to go, you only have to have a one-step horizon, right? And then conversely, the longer you make the horizon, the better performance you'll get in general, and the less reliant you are on the quality of your V of X approximation, right? Okay. Any questions about that? That's fairly okay. Cool. So now we're gonna do some stuff. We're gonna do a fun example that first I will take a minute to walk you through the example. I think this is probably healthy for people who haven't had a ton of exposure to dynamic stuff. So we're gonna play around with a planar quadrotor. And I'm gonna write you down the dynamics really quick before we go and look at it. So this will be, we'll have, you know, kind of center of mass. And then we'll have two little propeller guys over here. And let's see, we're gonna have a mass M, inertia J. We'll have gravity, usual G. And we're gonna call the overall kind of length here L. And then our coordinates are gonna be X, Y, and theta defined this way. And if I write down these dynamics, this is just F equals MA stuff, right? Super simple. I'm going to get mx double dot equals, oh, and I should say, yeah, the control inputs are U, thrust inputs here. So this is going to be U1 and U2 for two thrusters, right? And just like kind of eyeballing that, you'll find the following stuff. And I'll talk through this in a sec. So that's the X stuff. The Y stuff is U1 plus U2 cos theta minus mg. And then the theta stuff is J theta double dot equals torque. So this is 1/2 L U2 minus U1. Okay, so this is just F equals MA, right? So mx double dot, this is just adding up the U's, and then the sine theta is how much of that's tilted, right? And based on like the conventions I have for the definitions of theta and stuff, if U1 is bigger, I'm headed to the right, and if U2 is bigger, I'm headed to the left. And I think that sort of all lines up, right? Cool. And then what else? So yeah, and then the Y double dot stuff, it's U1 U plus U2 is giving me the total thrust. And then if cos theta is 0, I'm going straight up. So that kind of makes sense. And then mg is going down. And the last one is me taking like basically that cross product thing, right hand rule. So if U2 is bigger, I'm getting a positive theta, right, double dot. If U1 is bigger, I'm going the other way. So it's got a minus sign for U1. Any questions about that? It's just like really dumb kind of freshman physics stuff. Okay, so I'm going to do that. Then I'm going to linearize this about hover conditions to get our linear dynamics. And this is going to, so the first thing I need is our trim condition. So what is a condition? What controls do I need to hover this thing? Anyone tell me from looking at this? What should U1 and U2 be to get me to hover and sit still? Louder? So theta equals 0 also, right, for hover. So theta is 0, so it's U1 plus U2 has to equal mg, right? So U1 equals U2. equals 1/2 mg. And this is just doing gravity compensation, right? And then if I linearize the rest of everything, I'm going to get, I plug that in and I kind of do the rest. I'm going to get x. So these will be like delta x's, right? Deltas from hover. So delta x double dot is going to be approximately minus g delta theta. We got delta y double dot approximately 1/m delta u1 plus delta u2. And then delta theta double dot is approximately 1/j L/2 delta u2 minus delta u1. Okay. Anything, questions about that? So essentially, this is, I think it's important to point out here where the approximations are. The only approximations really that I made in the linearization were small angle approximations on the cos and sine, right? So keep this in mind for later, right? Basically, this is accurate as long as the angle is small. Otherwise, it should be pretty good, right? And then I can put this in my standard state space form with sort of the A and B matrix stuff, which we'll do just as an exercise, because I think it's a lot of you guys haven't done too much of this, so I'm going to do it to belabor it this one time. And okay, so this is my x dot. And then I've got an A matrix that's going to look like the following. So I've got, first off is just the velocity kinematics. So this is just, I should write down the state vector here is x, y, theta, x dot, y dot, theta dot. So the top is just zero identity block. The bottom is, if I look at this, the only non-zero term in there is this minus g multiplying delta theta in the top x double dot equation. The rest of this is zeros. And then this whole block is also zeros. So that's A. And then the rest of this is going to be in the B matrix. And this stuff's all zeros. And then the bottom row is basically just sort of here it's 1/m for the y double dot stuff, right? Multiplying, I should maybe write this, the u vector down first. This is going to be delta u1 and delta u2. And then the bottom row, I've got minus L/2 j, and then L/2j. Okay, so that's everything written in like standard state space form. This is the A, this is the X, this is the B, this is the U, this is the X dot. All right, so this is our standard X dot equals AX plus BU deal. By the way, these kind of like cartoonishly simple F equals MA models are super standard in practice. And like most of the models that you use for things like quad rotors and rockets and stuff basically look like this. They're really simple things. And they work super well, turns out, for a lot of control stuff. What else is there to say about this? The last thing is I'll be a little bit explicit about the cost function. So the cost function we're using is like the standard thing, but we're going to use like a sort of tracking cost where we've got a reference that isn't the origin. So just to kind of do that explicitly, it's going to look like this. We're going to have like a 1/2 xk minus x ref, where this is some reference, right? And that could be a set point, or it could be a time varying trajectory that we plug in. And then the other thing is the cost on the u's is the same thing. It's a u minus u ref thing, where the u ref is the hover u, right? The 1/2 mg. I'm going to just write that using deltas, since that's already kind of clear. And then lastly, we have the terminal cost, which again is going to be like x at the horizon minus x ref. And then this is our cost to go thing. Okay. All good? Questions, comments? Just trying to make this super clear. Okay, cool. So let's go do it. All right. So what do we got here? So here's our dynamic stuff. So this is, just putting in numbers. So G, mass 1 kilogram, 30 centimeter, L, whatever kind of, these are numbers are not particularly important. We'll talk about this in a sec. So I have this dynamics. Here are my control limits. So remember 1/2 mg for both propellers gives me hover. I made this 0.6. So basically I have 20% more than mg, which is actually pretty reasonable. Like that would mean, 0.2 mg positive acceleration straight up, which works out to be like 2 meters per second squared, which is pretty fast. So this is like still fairly aggressive. And then I put some lower bounds on this as well, because generally quadrotors can't spin their propellers backwards to generate negative thrust. And generally there's also a dead band. So you can't actually, you basically like usually there's 0 and then there's like, some level above 0, which is the minimum thrust you can actually produce because there's stiction and stuff like that. This is probably a little higher than what that is, but like there's always you basically don't want to actually run all the way down to 0 also in a lot of cases because of these dead band sort of situations. And then we're going to run at 20 Hertz. Here's my dynamics. This is exactly what we just wrote down, right? And then I'm actually going to plug this into the nonlinear dynamics into RK4, like we did at the beginning of the class. And then I'm going to be lazy. I derived all that stuff for you. It's on the homework, so you will probably still use that stuff. But here I'm going to use forward diff, auto diffing. I'm just going to diff through the RK4 step to get the discrete time A and B for the nonlinear system, right? So I'm plugging in the hover conditions. So 1/2 mg for the U's and then origin for the X's to evaluate this stuff at 20 Hertz through RK4. Cool. That gets me my A and B matrices. This is just some bookkeeping to set up the control problems, like 6, whatever. These are just, number of time steps, blah, blah, blah. That's not interesting. Cost weights, pretty much the same kind of stuff we did last time for Q and R. Multiples of the identity, really dumb stuff. Cost function, just adding it up. Okay, here's the LQR. So I'm going to do LQR, and we're going to compare MPC and LQR. So this is the LQR controller. I'm using the control toolbox that we talked about last time to get the infinite horizon LQR cost to go P, which I'm going to use in the MPC, right, for the terminal cost, and the infinite horizon K matrix from LQR. And then this controller, like just the kind of the standard linear feedback LQR controller. So I've got the hover term, right? Remember, this is all delta X, delta U stuff. So I've got U hover is the like nominal U, and then the delta U is minus K times delta X. The delta X is X minus my reference X. Does this make sense to everybody? Bunch of extra kind of bookkeeping in there. Okay, now we're going to do the QP stuff. So I'm going to walk you through this a little bit. We're using an off-the-shelf QP solver for this called OSQP, which is kind of the state-of-the-art, like really fast QP solver that's very widely used in online MPC applications. Like it's on lots of robots. So here's what this looks like. So this is the horizon. I'm actually, for comparison purpose, I'm going to set the horizon to 1 right now. So as we just talked about, that should make it basically match LQR, right? State and control and dimensions. So here's the way I did this, which is, you could do this a bunch of ways. But the way I'm doing it is we stacked up this vector like before when we did the QP, where it's got like x1, u1, x2, u2, x2, 3, 2, blah, blah, blah. So what I'm doing here is I'm defining these matrices to pull out all of the u's from that giant stacked vector. And then another one that we're going to use later that's going to pick out all of the thetas from that giant stacked vector for me to easily write down the constraints, right? This giant H matrix is that's bad notation overloading. This is the cost matrix. So it's just like block diagonal QR, QR, whatever, like we did before. What else is in here? And then this stuff is setting up the constraint matrices. So these are the dynamics constraints. You see like the A minus BI stuff like we did before. And then we're going to also add into this like for example, to do the torque limits, I'm going to do use this U matrix to pick out all the U's and then set the upper and lower bounds on them. So yeah, this is just a bunch of bookkeeping. Like it's the way OSQP interface works. Yeah, I think that's all there is to say about that. So you're going to use this on the next homework and do stuff very much like this. It's just the QP that we set up. It's just a matter of like kind of reading the OSQP interface, building all the matrices the right way, stacking everything up. There's in a million ways to stack this up. It's sort of arbitrary. This is just the way I did it. Any questions about that? Take a look at the code later. Okay, so here's the MPC controller. So just like the Lqr controller, what we're going to do inside here. So I'm going to plug in the current state, and I'm going to update the QP with the current state as x1, basically. And then we're going to resolve the QP, right? That's kind of the general strategy. So this is updating that initial state, the x1 in the QP, to be my actual current state in the right-hand side vector in the QP. The reason this looks funky is the way OSQP does it is everything's an inequality. So it's like AX, and then you have lower and upper bounds. And if you want an equality constraint, you set the lower and upper bounds to the same number, and it becomes an equality constraint, just quirk of the interface. And then I think that's about it. So I basically go through here and like update this stuff to match the current state. They have some special functions for doing this sort of updates to sort of warm start things. And then I go ahead and solve the QP. And then I take, U1 out of that, the first U, and that's the thing that I actually go run on the system. So that's that. Cool. Any questions about that? Okay. Then this is me doing a closed loop simulation. Not surprising here. So I just roll out the dynamics. And what I want to mention here is we're doing this on the real nonlinear dynamics. So we're not doing this rollout on the linearized dynamics. There's that. Okay, cool. So let's go do some stuff. Let's start with something easy. So I'm going to set my reference point to be 1 meter off the ground, but then everything else zeroed out. And I'm going to set my initial conditions to be like a meter off in the height and a meter off in the X. So that's what this guy is. Then I'm going to run both controllers, and we're going to look at what happens. So I'm going to plot a bunch of stuff. Basically, the point here is that these things, modulo small numerical errors and like solver tolerance, they match exactly. That's kind of the point, with a horizon of 1 on the MPC, right? So all this stuff's on top of each other. Yeah. Not super interesting, whatever. Let's go actually. So this is the fun part. Do some mesh cat. Go and look at this. So let me actually, you can visualize this. So this is like the Lqr answer. So we're starting, like a meter off, it's not very far. So this is not super challenging or anything. And both controllers work super well. Okay, so that's that. That's the straightforward stuff. Now we're going to try to mess around a little bit. So I'm going to go in and I'm going to make the initial error a lot bigger. So let's try like 5 meters here and see what happens. So yeah, as you can see, Lqr is now failing. Let's watch that in the visualizer. So Lqr is like, yeah, dying, not dual, not cool. And then MPC though, and keep in mind, this is still with only horizon 1, right? So it's working actually pretty well. And this is because the Lqr solution, right, with that big offset, it's maxing out the control limits, and it can't reason about this at all, right? So it's saying, oh, give me these big inputs, but the system's not able to do it, and hence crashing and dying and bad things. So here's what this looks like. But you'll notice, right, basically the MPC solution is like, Lqr is railing the actuators, right, on the hardware, but it doesn't know how to think about that at all. Whereas MPC like knows this is there and then is able to reason through it. So let me actually show you, like, if we, so I did horizon 1, which is terrible, right? In practice, I might do something like horizon of so I'm doing 20 hertz. Let's set the horizon to 20. So like 1 second would be kind of reasonable, right? So let's do that and let's rerun this and take another look. So it's still, obviously it works. It should work better. And in particular, if we look at this plot, we should see some like maybe slightly nicer behavior. Actually kind of looks the same. Never mind. Yeah, okay, so it didn't change much. Nothing surprising there. Let's see what else we want to do. Okay, so let's try to break this. Let's see how far we can push it. So I'm going to set the initial state error. Let's set it to like 10 meters and see what happens. So we'll rerun. So obviously LQR is doing terrible things. MPC is doing pretty well, it looks like. Still doing fine. Yeah, so it's, notice, right, it's saturating the controls a ton here. But again, yeah, the MPC controller like can actually reason about that. And it does okay. So that's all good. Let's like actually maybe go visualize a little bit what's doing. So, oh, I shouldn't have done that. That's the LQR just barfing. So here's the MPC controller. It starts way out there, but it sort of does some crazy stuff, but it's still stable. It doesn't crash. In particular, it's going like, it's taking a huge, bank there right out the gate, and it's going through the floor, which is maybe bad, right? So a pretty obvious next move here would be to put in a state constraint that says the height has to stay above the floor, which is you're going to do on the next homework, and play around with that. There's another thing I can do here, though, that I want to zoom in on real quick that's kind of interesting. So remember we said in the dynamics, the thing we were really approximating with our linearization was small angle approximation. So let's go look at that. So here's the angle state. I'm going out to like 1.25 radians and that. So I'm basically sideways at that point. And remember with that small angle approx, the reason we're going into the floor is I'm going basically full on sideways, at which point I have no thrust in the vertical direction at all. So I fall. But the linearized model doesn't have that in it, right? Because I made that small angle approximation. So the linearized model still thinks I have vertical thrust when I'm sideways, which is kind of intuitively what's going on here and why that's happening. But here's another trick I can play, right? I can actually go put a state constraint on this guy that says to keep the theta within a reasonable small angle approximation, right? So I can actually constrain my MPC controller to stay within the bounds of the linearization, like, error being reasonable. So let me go do that. I'm going to swap these constraints out real quick. So this is like another kind of cool trick to know about with these methods, right? Like I may be making these small angle approximations, but as long as I like don't need to do super aggressive stuff to achieve my goal, like my behavior, I can actually add state constraints to this problem to keep myself in a box of the state space that like is reasonable with respect to the linearization, right? So you can think, so I'm going to do here like 0.2 radians. So like, I don't know, like 10-ish degrees or so, right? Something like that. And we can now rerun this and see what happens. So super nice. So now, right, 0.2 radians. So now I'm staying in like a very reasonable place with regard to the linearized stuff. And let's go like visualize this and see what this looks like. So now, right, I'm not, oh, I still went through the floor. That's annoying. What's my height doing? I don't want to see this. Yeah, let's get rid of this. Huh. This should be, did I not update things? Maybe I, oh yeah, I didn't run, sorry. We're looking at the old stuff. Still have to run this. So that's LQR, we don't care about that. But here's the one with the updated stuff, right? So now I'm like doing this, I'm only allowing it to tilt, a few degrees, and I'm doing this nice, slow, gentle thing. I'm not going through the floor. I'm staying within like a nice region where my linearization is still good, all that kind of nice stuff. And you can, this game is like quite, like nice to play as a cool trick. Okay, anything you want me to try? Any other fun stuff? Otherwise, yeah, that's it for today. I'll hang out for